How is it that sugar is nature's armor plating? And why both natural fruit juices and soft drinks sweetened with high fructose corn syrup can lead to non-alcoholic fatty liver disease? I will answer those questions and more in this video. Hello, today's show is about one of the macronutrients. Macronutrients being, of course, protein, fat, and carbohydrates. Today's show is about carbohydrates. So carbohydrates, at least for the most important ones that I'll be talking about today, are made up of glucose. So carbohydrates are considered either a monomer, which is one molecule of glucose. There are a few molecules or monomers put together, and that's an oligosaccharide, try saying that once, and polysaccharides, which are many sugars put together, many molecules of glucose. Now, carbohydrates are called carbohydrates because of their chemical formula, and I can show that on the screen. I can say that it's CH2O, so it's a carbon and H2O, but it's a little bit misleading when you think of carbon just stuck to a water. So we can talk more about this, but it's mainly that the carbon has around it various orientations of things that make up water, oxygen and hydrogen. So they're kind of around the carbons that make up the sugar. And there are different types of saccharides, monosaccharides. There are some that are made with only 3 carbon atoms. There are some that are made of 5 carbon atoms. The 3s are called Triose, the 5 is called Pentose, and 6 carbons, which is what glucose is considered a hexose. That's not necessarily important for what glucose is, but it kind of helps to discuss the shape of the molecule and how it interacts with other molecules around it. With that 6 carbon structure, you end up with a hexagon, basically. And at each one of the points around that hexagon, there's a carbon. And off of that carbon are either an OH, hydroxyl group, or a carbonyl group, which is an oxygen, or hydrogen. So all these variations of types of things around it. And based on how these are oriented around that hexagon, you can get a different chemical structure and a different monosaccharide. So that's kind of interesting because there are so many variations of a saccharide. But for our discussion, glucose is going to be the most important one again. Okay, so there's a disaccharide called lactose that I'm sure you're aware of in milk. And lactose is made up of, it's a disaccharide, 2 saccharides, 2 monosaccharides stuck together, a glucose and a galactose. Now, when they're bonded together, they're called lactose. Now, lactose intolerance is where the person doesn't have the enzyme to break the glucose away from the galactose. And so that lactose stays intact. That enzyme is known as lactase. Okay, so that's a little excursion off of what we were talking about here. This next part is going to be a little esoteric, but stick with me. So there are 2 types of glucose. There is alpha glucose and beta glucose. There's an important aspect to this, so that's why I'm bringing it up. There's just a small difference between alpha glucose and beta glucose, and I believe it's on the first carbon where a hydroxyl and OH group is just simply flipped, which is a really small change, but it's enough to affect the way 2 glucoses are bonded. When 2 alpha glucoses are bonded, we have enzymes within us that we can break those bonds to liberate the individual molecules of glucose. If we eat starch, starch is made of alpha glucose, a bunch of those stuck together. So when we eat those, There's an enzyme called amylase that can break the glucose apart from that, and we can use up the glucose then as energy or fuel. The beta glucose, unfortunately, is not something that we can break up. Maybe not unfortunately, it's just that we can't. That type of glucose is found in fibers, which we'll talk about later. And there are a few rather common sugars that we might know about that we use in our food. Sucrose, which is one glucose and one fructose stuck together. There's fructose alone, like in high fructose corn syrup. Lactose, that's found in milk. And there's a rare sugar that you may have heard of called allulose. There's a lot of research coming out about allulose and its healthful effects, so I've been adding that to my food every once in a while. All right, so there are monosaccharides or monomers, and when those monomers come together, they can form either oligosaccharides, which are smaller sugars, or polysaccharides, which have numerous glucose, for what we're talking about right now, stuck together, bonded together. So of those polysaccharides then, starch is a big one. You probably all know about starch, and I think the biggest image that brings to mind is a potato or pasta or rice. So these strings of glucose are bonded in a way that they start to form a little helix. And then there's another section that starts to form branches. And those two are actually brought together to form starch. The coiled or the helixed variety is called amylose, and the branched version is called amylopectin. Now those two come together and they're kind of twisted and branched, so it's a really dense configuration of glucose molecules stuck together. And that's why there's so much of a rise in insulin and why insulin stays so high when you eat starch. So that's kind of a drawback of eating starch. These branches occur about every 30 molecules of glucose. So you have 30 glucose, now there's a branch. Another 30 and there's a branch. So that's going to come up kind of interesting when I talk about glycogen. So again, what we talked about earlier is that to break up starch, we need an enzyme, and that enzyme group, or that type of enzyme, is called amylose, or amylase. Now, amylase exists in our mouths, in our saliva, and it's also produced by our pancreas, so that we can break up sugars, starches, all the way through our digestive system. So glycogen then. Glycogen is the storage form that our body uses for quick energy. And that glycogen is stored in our muscles and also in our livers. And so when we're exercising and we need energy really quickly, we have some enzymes that break up that glycogen and start popping off glucose to send into the entire cellular respiration cycle that we talked about in a couple shows ago. So I'd recommend looking that up. The glycogen is another branched chain of glucoses, but glycogen is even more dense than starch. Glycogen has a branch about every 10 glucose molecules instead of the every 30 molecules that starch does. So it ends up being a lot more dense. So that brings us now to cellulose. So cellulose is also glucose molecules stuck together, but cellulose is that variety that I talked about earlier, beta glucose. The starch and the glycogen are both made up of alpha glucose. So those alpha glucose bonds are easier for our enzymes to break apart so we can get the glucose to make energy with. Cellulose, on the other hand, is made up of beta glucose, and beta glucose can't be broken up with the enzymes that we have. But things like cattle, ruminants, and gorillas can deal with those types of bonds because they have digestive systems that include a number of bacteria that can actually break those bonds fairly easily and form fatty acids, fats, and protein. And those fatty acids and proteins then are used by the cow or the gorilla to get really big and muscular. Gorillas, I think I've heard, they eat like 40 pounds of fiber a day, and they poop about 40 pounds of fiber a day. But that's how much it takes in order to keep them big and strong. Where cows are ruminants, they have 4-chambered stomachs that do all this strange stuff. Gorillas have a similar digestive system to us, but similar is even too close. It is massively different. We have long, small intestines. Those small intestines, with the high acid in our stomachs, are used to break up proteins and fats and digest those properly, along with the bile from our gallbladders. Gorillas have a digestive system that is almost the opposite. Instead of having a lot of small intestine and very short colons, like we do, relatively short colons, gorillas have very little small intestine and a lot of colon, a lot of large intestine. And in that large intestine are the bacteria that can break up the cellulose into the fats and proteins and keep the gorilla alive. So we are completely different when it comes to how our digestive systems evolved. All right, so then there's another polysaccharide called chitin. And chitin isn't really made of glucose, which I've been talking about glucose, but it's a very important polysaccharide. It's made from a monosaccharide called N-acetylglucosamine. It doesn't really matter about that. It's just that it is another polysaccharide. It is a hexagonal sugar molecule, but it has some other stuff hanging off of it instead of just the oxygens and hydrogens. And the result of that is that chitin is incredibly hard and strong. And you'll know chitin as the exoskeletons on insects and crustaceans, like that lobster you have to break open. That's chitin. That is just a polysaccharide. It's amazing. When you can think of that, it kind of boggles your mind. This is just a sugar that's bonded together, but that's exactly what it is. It's a different kind of sugar than glucose, but it's still just a sugar. All right, so we've talked about monosaccharides or monomers, oligosaccharides, which are just a couple of monomers stuck together, and polysaccharides. And I would like to talk a little bit about another sugar that's really important to know about, and that sugar is fructose. I know that I'm guilty of thinking or being told that fructose is a lot more healthy than eating table sugar or kinds of sugary snacks. It's better to drink fruit juice than to have a Coke. And that is anything but the truth. So fructose is handled differently than glucose. As we know, sucrose is one glucose and one fructose stuck together. So when you eat table sugar, you're getting a double whammy. So with glucose, we are regulated on how that is handled. The liver has receptors that allow glucose into it to do the processing. And the processing itself is regulated by insulin and some other things so that it doesn't get out of hand. Simply when there's an abundance of glucose in the liver simply takes that glucose, sends it through the glycolysis, and then from that glycolysis, the pyruvate goes into the mitochondria, as we talked about before. And once it gets into the mitochondria, it turns into acetyl-CoA. That acetyl-CoA then is brought back into the cell's cytoplasm, where it is converted into triglycerides. And those fats, those triglycerides then are packaged up into these little things called very low density lipoproteins, VLDL. You'd know LDL, which is low density lipoproteins. The VLDLs are sort of precursors to those. They're sent out into the body by the liver. Fat cells kind of take up the triglycerides that are in them for storage, and they slowly become smaller, going through an intermediate density lipoprotein, and then go to a low density lipoprotein. That's kind of blah blah. Anyway, so all of that process is regulated, highly regulated, but fructose is not regulated. It just comes into the liver because the liver is the only organ in our body that can deal with fructose. So it's the only game in town. And in order to get fructose out of our systems, unlike glucose, where glucose can raise the ability of GLUT4 transporters and other kinds of glucose transporters to bring it into muscle and other types of cells, as well as the liver. With fructose, the liver is the only organ that can deal with fructose. So the liver gets overwhelmed if there's a lot of fructose, which you'd get if you drank just even a small glass of apple cider or apple juice. Even if it's unsweetened, there's a lot of fructose. If you have like a 5-ounce glass of apple juice, it's like eating 4 apples. I mean, who can actually eat 4 apples? Not many people, and not very often. So you're getting this huge influx of fructose. So the liver has to take this fructose, and it does a whole bunch of things to it, but it ends up creating this acetyl-CoA once again. And the acetyl-CoA then turns into, or is processed to become a triglyceride. But because the liver is overwhelmed by all this fructose, it doesn't have time, and it can't ship this stuff out in those VLDLs. So these triglycerides, this fat, ends up building up in the liver. And we see this because I think it's 5 or 10% of children now have non-alcoholic fatty liver disease. And it's likely due to all of the fructose that kids are getting nowadays in, these little fruit snacks, fruit roll-ups, fruit juice. Parents they want to give their kids good food instead of having them drink Coke a lot of times. So they'll give them, here, have some orange juice, have some fruit juice, grape juice, all this, but it's filled with fructose. And the fructose is causing 5 to 10% of children to end up with non-alcoholic fatty liver disease. And that is really dangerous. So we need to really watch this. But not only does fructose affect the liver by building up fat, fructose also contributes to the breakdown of the tight junctions in our intestines, causing leaky gut syndrome. So tight junctions, in our stomachs, we have the epithelium, the epithelium that are stuck together. The epithelium are the cells that line the inside of our intestines. So those epithelium cells are bonded together by these things called tight junctions, and they're proteins that sort of sew the cells together. fructose acts directly on those proteins that form the tight junctions and break those tight junctions, so that now you end up with leaky gut and inflammation and all sorts of other problems. So fructose, what I used to think was really the most healthy sugar you could ingest, I'm now realizing that that stuff is poison if you take too much of it. Now, if you take it in a normal dose, you have some honey in your coffee, like a teaspoon or two, or you eat a fruit, an apple, a banana or something, that much isn't going to overwhelm your liver. But when you take a full glass of juice, fruit juice, or multiple cans of some sort of sweetened soft drink, you're overwhelming your liver, and it's going to hurt your liver, and it's going to hurt the tight junctions in your intestines and cause all sorts of problems there too. So fructose, you've got to be careful with it. In moderate doses, in small doses, I should even say, in small doses, it's fine. All right, so I think that might just about end my conversation about the micronutrient called carbohydrates. Once again, carbohydrates are considered polysaccharides or oligosaccharides, or just a monomer, a monosaccharide. And I've talked a little bit about de novo lipogenesis, the formation of fat from brand new that happens in the liver with fructose. When it happens from glucose, it's all regulated, so that regulation, even though it may develop a buildup of fat on your body, at least it's not contributing to non-alcoholic fatty liver disease the way fructose does, as fructose forms that fat from the de novo lipogenesis within your liver, overwhelming the liver so it can't shuttle that stuff out of there, and you end up with fatty liver disease from stimulating or overfilling your liver's capability of dealing with that fructose. So I hope this was helpful, and I will see you next time. Thank you for listening to Seeds for Health. I hope the information that I presented was informative. If so, please hit subscribe. Please also leave comments on how I can improve or topics that you'd like to see covered. Enjoy your journey to better health, and I'll see you next time. Thank you.